Picture this. You're on a massive cargo ship in the middle of the South Atlantic Ocean. It's 3 in the morning. The temperature is below freezing. The waves are 40 feet tall. Then, without warning, the ship begins to list. The engines go silent. The hull is flooding. You have exactly 4 minutes before she goes under. And the only thing standing between you and 2 miles of black water is a small orange capsule bolted to the side of the ship. Now here's the question nobody ever thinks to ask until it's too late. Who designed that capsule? How does it survive conditions that tear steel apart? And most importantly, will it actually work when you need it most? The answers to those questions are more fascinating, more terrifying, and more brilliantly human than anything you've ever heard in a safety briefing. Stay with me, because this story starts with the single worst engineering assumption in maritime history. Most people know the name Titanic. What most people don't know is that the Titanic's lifeboats were not broken, not defective, and not poorly built. They were designed for a world where ships couldn't sink. That was the assumption that killed over 1,500 people on a single April night in 1912. The lifeboats were wooden, open-top, and human-rowed, built for calm harbor evacuations, not mid-Atlantic survival in freezing water. They weren't even filled to capacity on the night of the disaster, because the crew genuinely did not believe they would be needed. This wasn't incompetence. This was the engineering mindset of the era. And after April 15th, 1912, that mindset was finished. The International Convention for the Safety of Life at Sea, known as SOLAS, was born the following year, demanding that every passenger vessel carry enough lifeboat capacity for every single person on board. But here's the uncomfortable truth that took another 60 years to fully admit. Having lifeboats is not the same as surviving in them. Open wooden boats in freezing seas were still death traps. People were dying of hypothermia before rescue ships could arrive. And so began one of the longest, most quietly extraordinary engineering challenges in modern history. How do you build a vessel small enough to hang off the side of a ship, but powerful enough to survive the ocean itself? The modern lifeboat looks absolutely nothing like what most people picture when they board a cruise ship or a ferry. It is not a rowboat. It is not even in the same category. It is a fully enclosed, fiberglass reinforced survival capsule engineered to tolerances that rival aerospace equipment. And when you understand exactly what it has to survive, you begin to understand why every single detail of it exists. Start with the hull. Modern lifeboats are constructed from high-density fiberglass composite panels, the same broad family of materials used in military vehicle armor and racing yacht hulls. That hull must absorb the impact of being dropped from a height of 18 meters, nearly 6 stories, into churning open seawater, fully loaded with the weight of its maximum passenger capacity, without fracturing. Every certified lifeboat goes through standardized drop testing before it ever reaches a ship. Engineers load the vessel to its rated capacity, drop it repeatedly off an elevated platform into water, and measure stress concentrations at every structural joint and panel seam. One failure is one too many. The product doesn't go to market. Now look at the shape. That distinctive rounded, almost egg-like form isn't about aesthetics. It's about physics. The rounded hull geometry combined with the carefully calculated weight distribution of the engine, fuel tank, and seating allows the vessel to self-right automatically if a wave capsizes it. Even if a 40-foot wall of water flips the lifeboat completely upside down, the hull will rotate back to upright position within seconds, with the passengers still strapped inside. That feature alone has saved an estimated thousands of lives across modern maritime disasters, and it didn't become standard in lifeboat design until the 1970s. Before that, a capsized lifeboat was simply a coffin. Now think about the propulsion. Modern enclosed lifeboats carry diesel engines capable of pushing the vessel at 6 knots in open water, roughly 7 miles per hour, which is enough to move the craft well clear of a sinking ship before the downward suction and underwater turbulence pull everything nearby beneath the surface. The engine air intake system is sealed against complete wave submersion. The fuel system is shielded. The propeller is mounted inside a protective shroud so it can generate thrust even when partially lifted out of the water by waves. And here is the engineering detail that almost nobody outside the maritime industry ever hears. The entire propulsion system is designed to function even when the lifeboat is inverted, because the engineers who built it understood that in a real disaster at sea, you may not have the luxury of waiting for the hull to right itself before you need to move away from a burning, sinking vessel. Step inside a modern survival lifeboat, and you are stepping into a space that was designed by people who studied, in forensic detail, every single way human beings die at sea. The seating arrangement is not about comfort. It is about survival biomechanics. Passengers are seated facing rearward in padded harness restraints, the same orientation used in military transport aircraft, because rear-facing seated passengers sustain up to 40% fewer spinal injuries during violent water impact than forward-facing ones. The interior walls are insulated to retain body heat even in sub-zero ocean temperatures, because hypothermia remains one of the leading killers in maritime survival scenarios. There is a hand-operated bilge pump, a sea anchor to stabilize the vessel in extreme wave conditions, a VHF emergency radio, visual signal flares, a basic first aid kit, 3 days of emergency rations, and a fresh water supply calculated per person per day. There is also a fishing kit, because rescue is not always measured in hours. Sometimes it is measured in days. Now here is the part of the story that takes everything one level further. The Freefall lifeboat. In conventional lifeboat systems, the vessel is lowered down the side of a ship on cables using a mechanical davit. That system works under normal conditions. But on offshore oil platforms, where the threat isn't a flooding hull, but an explosion or a fire, those cables become lethal. A blast can destroy the lowering mechanism. A fire can burn through the cables before the boat reaches the water. So engineers designed an entirely different solution. The Freefall lifeboat is mounted on a steep, angled ramp at the stern of the platform. When the release mechanism is triggered, the vessel slides down the ramp under its own weight and launches directly into the sea like a projectile. The entire sequence from trigger pull to water entry takes fewer than 8 seconds. Passengers experience a peak impact force of roughly 15 times the force of gravity on water entry. Engineers describe it as survivable but violent. And immediately after water entry, the engine fires automatically and the vessel begins moving. No cables, no davits, no external mechanisms that can be destroyed by the exact emergency you are escaping. This technology is not experimental. It is the operational standard on virtually every offshore platform in the North Sea today. But here is the truth that no engineer will say publicly, and that every maritime survival researcher knows deeply. The most dangerous component in any lifeboat system is the human being attempting to operate it under conditions of complete terror. Decades of disaster analysis consistently show that most lifeboat deployment failures are not mechanical, they are human. Panicked crew members cannot operate equipment they only rehearsed once a year. Passengers freeze on gangways, decision-making collapses under adrenaline, leaders give wrong orders. And so the newest frontier in lifeboat engineering is not materials or propulsion, it is human factors design. Release mechanisms are being simplified to require the absolute minimum number of cognitive steps. Controls are color-coded and physically intuitive. Auto-sequencing systems are being developed that remove decision-making from panicked hands and transfer it to the machine. The future goes even further. Fully autonomous lifeboats with GPS self-navigation that can pilot toward the nearest rescue coordinate without any human input are already in advanced development. Thermal detection systems capable of locating survivors in the water and dispatching unmanned rescue craft automatically are currently in testing in Norwegian waters. And materials engineers are developing self-healing composite hull panels embedded with microcapsules of structural resin that automatically seal small breach points on impact. The lifeboat of the next decade will not need a calm, trained, decisive human being to save your life. It will do it regardless. The next time you board any vessel and walk past those orange capsules hanging off the side, don't look away. Don't treat them as wallpaper. Every seam on that hull, every harness in that cabin, Every sealed fuel line and shrouded propeller and automatic release mechanism exists because someone died before it did. Every engineering solution in that capsule was born from a failure that cost a human life. That is not a grim thought. That is the most honest form of respect that engineering ever produces. The stubborn, meticulous refusal to let the same death happen twice. The ocean has never once agreed to be kind, and the people who design lifeboats have never once stopped designing anyway.